Okay, chapter 11.2, permutations. In the previous section, we filled in blanks and used the fundamental counting principle to determine the number of ways something could occur. Such an ordered arrangement is called a permutation. In a permutation, no item can be used more than once, and the order of arrangement makes a difference. Let's look at an example. If you were to arrange 15 different books on a shelf, and it took you 1 minute for each permutation, each arrangement, how long would it take you? Okay, well, I've got 15 books, so that's 15 spaces that I have to fill in with a book. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in the first spot, I have 15 choices, 15 books to choose from. I put one in the first spot. Once I put a book in that first spot, on the next spot, I only have 14 choices that I can choose from. And then once I put a book here and a book here, there are only 13 books left that I can choose from, and so on. And then there's 12 and 11. And of course, my fundamental counting principle tells me I need to multiply every one of these possibilities until finally, on the last spot, there's only one book left. So if I put this in my calculator, it is going to be such a big number that my calculator gives me that answer in scientific notation. So be sure, if you have any questions about how to read your calculator, be sure and let me know. Let me show you what mine says. Mine gives me this as an answer for this problem. 1.307674368, and then it has this weird E with a 12 after it. That means, excuse me, this number was too big to fit on my calculator screen. And it's given it to me in scientific notation, where this is the exponent on the 10. So that means I need to move my decimal place 12 units to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I need to fill in 3 zeros on that number. So that's how many possible arrangements there are for 15 books on a shelf. If each arrangement took me 1 minute, this is how many minutes. What do we have? Millions, billions, trillions. So 1 quadrillion, 307 trillion, 674 billion, 368 million minutes. I wonder how many years that is. Well, let's convert it. Let's do our dimensional analysis. So I know that there are 60 minutes in an hour. I want the minutes on bottom, remember, so that it'll cancel with this minute. And then I know that there are 24 hours in a day. And then I know that there are 365 days in a year. So if I do that math, I'll have my answer in years. So I need to take this number and divide it by 60 times 24 times 365, and I get 2.6 7964.9. Whoa! Nearly 2.5 million years. 2.5 million years to arrange 15 books on a shelf if every possible arrangement took 1 minute. That's kind of a big number. Okay, the product in the above example is given a special name. It is called 15 factorial, and it's written like this. Okay, in general, if n is a positive integer, then n factorial is the product of all positive integers from n down through 1. So notice n factorial would be n and then 1 less, 2 less, 3 less. So for our example above, 15 times 14 times 13 times 12, times 3 times 2 times 1. And also the definition of 0 factorial. 0 factorial is just understood to equal 1. Okay, there's one arrangement, one way you can arrange nothing. So, you need to find this exclamation mark on your calculator. So pull out your calculator. And again, if you have any issues with your calculator or where to find something or how to interpret it, be sure and let me know. You will be looking for a couple of things. You could just have the factorial on one of your, probably on your second button. It probably won't be on a key, but it could be. You could be looking for something that looks like this just on the face of your calculator. More than likely, you have either a math button on your calculator somewhere or some kind of probability button, PROB, PRB, something. You may have a combination of these, like my graphing calculator. I have to go into math, and then I have a probability option inside math. So hit your math button. If you just have a list of symbols, go down and look for the exclamation mark. Okay. If you have a probability button, do the same thing. Or if your math button takes you to options and you have a probability, look in there, looking for the exclamation mark. Okay, so you might want to test that and maybe make sure that you know how that works. For example, if you were to do 5 factorial, find that in your calculator. And see if you get 120. If you can't find it, please contact me. Now, we also need to be able to evaluate some factorials without using a calculator. For example, let's start with this one. Let's say you found your factorial button. Punch this in your calculator. 500 factorial divided by 499 factorial. Okay, I get an error message. It says error overflow. These numbers were too big for my calculator to calculate. So I do need to rely on some basic math when calculating some of these values sometimes. Think about what 500 factorial means. 500 factorial is 500 times 499 times 498 times 497 times 3 times 2 times 1. And 499 factorial means 499 times 498 times 497 times times 3 times 2 times 1. Since everything is multiply in the numerator and denominator, remember anything that's the same in the numerator and the denominator can cancel out. So really, one way to have written this was 500 times 499 factorial over 499 factorial. Right? Notice every one of these, the 499, 498, 497, all the way down, is going to divide out. And hey, that's only 500, even though my calculator could not calculate that. It was a very simple calculation to do by hand. All right, let's try this one without using a calculator. Okay, I'd have 8 times 7 times 6. But once I get past 5, since there's a 5 factorial in the denominator, that 5, 4, 3, 2, etc. will divide out. So all I have to do is write 5 factorial and then divide by 5 factorial. Anything that's the same in the top and bottom will divide out, and I am left with just having to calculate 8 times 7 times 6, or 336. Okay. We've got this notation right here, which means the number of permutations of n things taken r at a time. And your formula looks like this. Notice we were just practicing with dividing some factorial notations. This is why. Now, technically, I never use the formula for permutations. Instead, I fill in the blanks. In the next section, we're going to have something called combinations. Permutations and combinations are very confusing to keep straight which is which. And I have a formula for combinations that's very similar to this. So I think it's easiest to keep my permutations and combinations straight if, instead of using this formula for permutations, I always think of, oh, a permutation, that means I'm filling in the blanks because that's an arrangement and my fundamental counting principle, instead of using the formula. Okay, let's look at the number of permutations of the letters in the word set. Okay, let's see all the different arrangements that I can make. I can do S-E-T. Right, there's one arrangement. I could trade places with the T and the E. Okay, and then I could put the E first and have the S-T, the E first and have the T-S, or I could put the T first and have the S-E and the T first and the E-S. So yes, there were 1, 2, 3, 4, 5, 6. Notice that's 3 factorial. Notice that is the letters in the word set. There's 3 letters in the word set. The first choice, I have 3. I can put an S, I can put an E, or I can put a T. But once I've put either my S here, or my E here, or my T here, then there are only 2 left, and then 1. So either way I look at this problem, right? It's a permutation of fill in the blank because it starts at a number and multiplies down by 1 all the way to 1. I can plug 3 factorial in my calculator. Or with this one, I can literally see what the 6 different arrangements of the letters are. But let's think about the permutations of the letters in the word B. Okay, so I have the B-E-E, just like up here I had the S-E-T. And then what I did was I left the B, well in this case the S, the first letter the same, and changed the arrangement of the second ones. But notice if my word is B, when I move the E-E, I don't really get a different arrangement. Okay, so then what I did is I moved the E to the front, the second letter to the front, and then I had a B, a B, E, or if I move the E to the front, sorry. Okay, and then change these two. Could have E, B, Now that one is different. Then move the third letter to the front. Okay, and have BE. Wait a minute, that's no different than that. Okay, and then change those two, EB, and this is no different than that. And we already said this is no different than that. I did not get 6 different arrangements of letters. I only got 3. So, when we are doing permutations of duplicate items, or you might call it like things, if any of the items are the same, we've got a special formula for that, okay, which looks like this, where P and Q and R are identical. So, for example, here's my formula that I have to memorize for distinct permutations of like items or duplicate items. In this case, the n factorial, I did have 3 letters. So 3 factorial on top. But then the 2 e's were the same over 2 factorial. I really like to extend this idea and say, well, let's put for every single position 2 e's and 1 b, and this is going to help me with my formula in the next section also. These numbers down here better add up to be the same as this number. And we can see again, I can plug that on my calculator, but that's such a simple one that I don't need my calculator because that 2 factorial is going to divide out and leave me 3, which, yes, we knew that's how many we should get. So let's do, for example, the word door. Okay, well, there's 4 total letters. There's 1 D, 2 zeros, sorry, O's, and 1 R. Here is how to calculate the number of different, distinct permutations. Okay, so 4, of course 1 factorial is just 1, so I have 4 times 3 times 2 factorial, and then 1 times 1 times 2 factorial, or 12. Okay, let's get some practice on this. Six performers are to present their comedy act on a weekend evening at a comedy club. How many different ways are there to schedule their appearances? Oh, well, okay, there's 6 performers, so I need to fill in my blanks. 1, 2, 3, 4, 5, 6. Okay, now, how many different ways are there to schedule their appearances? Well, I have 6 choices that could go in my first slot, but after I've put 1 performer in the first position, I only have 5 to choose from, and then 4, and then 3, and then 2, and by the time I get to the last slot, there's only 1 choice. So I can type that in my calculator, 6 times 5 times 4 times 3 times 2 times 1, or I can just find my factorial key and hit 6 factorial. To get that there are 720 different ways to schedule their appearances. As above, 6 performers are to present their comedy acts on a weekend evening at a comedy club. One of the performers insists on being the last stand-up comic of the evening. If this performer's request is granted, how many different ways are there to schedule the appearances? Now, here's just one example of the many ways that thinking of permutations as filling in the blanks will help me. I still have 6 performers, but I have this special request. One guy wants to be last. Always fill in your special request first. So if he insists on being last, then there's 1 person that can go in the last spot. Now, that looks the same up here, but think about this. If I have to put this guy in that spot first, then when I go to choose how many people are going to go first, there's only 5 to choose from. And of course, once I've put one in this spot and I already have this guy in last, there's 4, and then 3, and then 2, and then 1. So 5 factorial is the number of ways that you can arrange their performances if you have a special request, or 120 different ways. You need to arrange 9 of your favorite books along a small shelf. How many different ways can you arrange the book? Assuming the order of the books makes a difference to you. Order is important to keep in mind when you're talking about these counting methods. So 9 books, we already did a problem similar to this, except instead of 15, we have 9 blanks to fill in. 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice I can choose 9 books. After I've placed one in the first position, there's only 8, and then 7 all the way down till that last book is in the last position. So 9 factorial is 362,880 different possible arrangements of your books. Okay, evaluate each expression. Be very careful with our factorial expressions. This is not 4 factorial, right? If I'm not dividing, right? It's subtracting. So I have to put this on in my calculator separately. I cannot simplify this. This is 4 factorial, right? So this one I can enter as 4 factorial. This one I just have to put in as 7 factorial. And I can do the numbers individually, but I'm plugging it in a calculator anyhow. I don't really need to do that. So 7 factorial minus 3 factorial gives me 5,034. Now this is 4 factorial, right? I could plug it in my calculator just like this if I'm careful with my parentheses, or I can evaluate 7 minus 3 and get 4 factorial, or 24. Now this one, because it's a divide, I can do 7 factorial over 5 factorial, which is 7 times 6 times 5 factorial over 5 factorial. 7 times 6, 42. Okay, now I've got a couple of choices on these. I can either go back and recognize what this means in terms of my permutation formula, which is 8 factorial over 8 minus 5 factorial. And then plug that in to my calculator, or do the 8 factorial over 3 factorial. Or I actually also have a specific button for this factorial, for this permutation. So again, if you had a math or a probability button, probably in the same place you found your factorial button, you should have seen this formula in there. You will probably have to punch the 8 first and then go into your probability or math part of your calculator and then hit 5 and hit equal. So let's see if we can all do that. And it'll probably look like this because your calculator isn't really capable of making those smaller. It should look like this. And you should get 6,720. The same thing you'd get if you did 8 factorial divided by 3 factorial. All right, so let's try this one. Okay, hit the 6, go into your calculator, and find your permutation, and then hit 6 again. And you should get 720. Or, plugging into the formula, it would be 6 factorial over 6 minus 6 factorial. 6 minus 6 factorial. So 6 factorial over 0 factorial. Remember, 0 factorial is understood to be 1, so it's basically just 6 factorial or 720. Let me know if you have any issues with your calculator or need any help with your calculator. Yeah, as you can tell, you are not going to be able to do many of these problems without the help of your calculator. Okay. How about this? A club with 10 members is to choose 3 officers: president, vice president, and secretary-treasurer. If each office is to be held by one person, and no person can hold more than one office, in how many ways can those offices be filled? Well, because there's 3 offices, that gives me 3 blanks to fill in: president, vice president, secretary, treasurer. Okay, there's 10 members, so I've got 10 choices that could be president. But once someone is president, he cannot also be vice president, so that leaves only 9 choices for vice president and then 8 choices for secretary treasurer. So 9 times 8 is 72 with 1 0, 720 ways those offices can be filled. 9 brands have volunteered to perform at a benefit concert, but there's only enough time for 5 of the bands to play. How many lineups are possible? Okay, well, there's only 5 slots to fill. Okay, but 9 bands have volunteered, so I can choose from any one of those 9. I got 9 different options to put in this first slot. But after I have filled the first slot, then there's only 8 bands to choose from. Then there's only 7, and then there's only 6, and then there's only 5. Notice this is not a factorial question. These questions aren't always, oh, this one wasn't either, right? These questions aren't always all the way down to 1. That's why filling in the slots is really beneficial, I believe. So I just have to type 9 times 8 times 7 6 times 5, and I get 15,120 possible lineups. And how many distinct ways can the letters of the word Dallas be arranged? Uh-oh, some of these letters are the same. I've got to know that formula for permutations of like items or duplicate items. So first of all, it's count the total number of letters, 1, 2, 3, 4, 5, 6, or items, whatever it is, and that goes on the top. And then I think it's easier to just remember there's 1 D, there's 2 A's, there's 2 L's, and there's 1 S. Now, as a double check for me, 2, 4, 5, 6, these numbers better add up to my top number. Okay, so I've got a couple of choices here. I can enter that in my calculator like it is, or I can work on it a little bit and simplify if I want to. 6 times 5 times 4 times 3 times 2 factorial, which means now I know 1 factorial equals 1, so I've got a 2 times 1 times 2 factorial left. That'll divide out, right? The 4 and the 2 will divide out, which gives me 30 times 2, 60 times 3, 180, or I can plug that in my calculator, 6 times 5 times 2 times 3. Or I can plug all this in my calculator. Just make it easy on yourself. How many distinct permutations can be formed using the letters of the word Tennessee? Again, some of them are the same. So start out by the total number of items. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then let's see, there's 1 T, there's 4 E's, there's 2 N's, and 2 S's. As a double check to make sure I've accounted for everything, 4, 5, 6, 7, 8, 9. Yes, this total better be the same as what's up there. And again, instead of going to all the trouble, because it's kind of a pain to get to that factorial button, so I might help myself a little bit by simplifying these factorials. I notice I got a 4 factorial in the denominator, so that's just 1. So if I put that 4 factorial in my denominator down here, I've taken care of that. And then 2 factorial is just 2 times 1 and 2 times 1, right? I got two factorials down there. So this divides out. Okay. This 6 and that 2 divides out. And this 8 and that 2 divides out. So all I have to really put in my calculator is 9 times 4 times 7 times 3 times 5. Easier than going in and finding that factorial button over and over. 3,780 different arrangements for the letters of the word Tennessee. Okay, combinations is next up, so keep in mind what it means to be a permutation before you start the next section.